Right. Thank you everyone for coming. Really appreciate your commitment to knowledge during January, during the break period. So my name is Artem. I'm currently a PhD student here in CSAIL. I work somewhere in between graphics and vision. So I'm really curious about all the stuff in 3D. How do we perceive the world? How do we understand the perspective? How do we map it in our brain? And how computers can do this? So today we are going to talk about score distillation. This is like a little branch or per se application of diffusion models. And I think it's very exciting. So I hope you'll think the same way after the lecture. There is quite a few material slides in here, so we might not go through all of them. But feel free to ask questions if you get lost or if you zone out. Just raise your hand. It's fine. I think it's okay to skip through some of the material in the end. So just a little reminder, we had 4 lectures before this one, right? So Chenyang started by introducing a diffusion model, right? So we know what's it doing roughly whenever it's denoising the objects. It's moving our image towards the data distribution and then assigns, depending on the time step t, to somewhere to one of the data points. Then Cole continued with samplers and more formal derivations. So I hope you remember what is DDPM and what is DDIM, what's the difference, right? DDPM is a stochastic sampler of images. DDIM is very similar, just we remove the noise term and we sample images deterministically. Cole continued with the regressive perspective. Then Boyuan introduced conditioning, right? So what if we want to sample images based on our text prompt, based on other images, or based on whatever we want to generate. And finally, Chris was talking about why do they generalize, right? If you remember, there is a big question, why do they sample something apart from the images in the training data set, right? If you analyze the minimizer of the loss, it seems to be not so trivial. And so finally today, we'll be talking about score distillation. So this lecture is going to be built like this. I'll start with just introducing a rough, hand-wavy explanation of how it works. And then in score distillation, at least in the original paper, it's called Diffusion, there were a few caveats. It was not that clear why it works the way it works. So we will go through 3 different derivations, 3 different perspectives on how to view it. And I hope that the last one, at least for me, also partially because it's my paper, it's the most intuitive one. And then we'll see how to apply this in different scenarios apart from 3D generation. But what are we trying to solve, really? What is score distillation? Or maybe before we go there, does anyone have an intuition what it can be? Just looking into the words, score distillation, what can we do with this? Any ideas? Can you raise your hand if you remember what is score? All right, well, that's fine. We'll go over it. But basically, score in diffusion models, right, in statistics, by score, we usually understand the gradient of the logarithm of the distribution, probability distribution. So if you remember all this scary math from the homework or from the derivation from lecture 2, usually when we work with diffusion models, we work with the gradient of a logarithm of the probability distribution in image space, right? And so typically, this gradient of the logarithm, we call it a score. And score distillation is something right, so something around taking this score and applying it somewhere else. And the same, if you remember, the objective that we use to train the diffusion model is called score matching. And why it's score matching is because we take one noise from one diffusion model, take another noise from another diffusion model, we try to match them with a L2 loss. So anyways, this is just some intuition from the start. So what are we trying to do? We know that all the diffusion models, they work amazing on image generation task. So we can take some noise, we can fine-tune some UNet, and run it through this network, and it will generate us a cat. What if we want to do the same for 3D? What if we try to generate 3D shapes? So maybe we can take some kind of concept of 3D noise, adapt our architecture of the neural network to take the 3D noise and generate 3D shapes, and hopefully generate a 3D cat. Well, the problem with this approach is that how many images we have in the internet. So there are like a few data sets that are billion scale, right? So like this line 5B that contains many billions of images, but how many 3D shapes do we have available to us? Like the biggest data sets are usually on the scale of like 100,000 at most. And so while you're increasing the complexity of the task, you want to generate more complicated objects than just images. You have much less data available to you. So we probably need to consider some other methods than just naively scaling all to three dimensions. And this is really what score distillation is about. So there was a work, Diffusion, but to be fair, there were like multiple works at the same time, approximately 2 years ago, that introduced the same idea. Why don't we take a pre-trained diffusion model and try to do something with this? So in particular, we'll start with some kind of like 3D shape container. Can you raise your hand if you know what a nerf is? Not like the gun, but okay, not many. So nerf is basically, you can think about it as a differentiable 3D representation. It doesn't really matter how it works. There are like multiple, there's like Gaussian splattings that is very famous right now. But the idea is that you can take some 3D shape and parameterize it such that whenever you render a shape, so like you put a camera around this data structure, and with this camera parameters you can create an image, like a rendering of the 3D shape. And this rendering, what's most important? This rendering will be differentiable all the way back to the data structure. So it means that you can backpropagate information through this rendering procedure. And this is really what we need. Like we just have some differentiable 3D data structure. So okay, we took this differentiable 3D structure, we initialize it to like a random blob or whatever, or like a sphere. We randomly sample a camera around the sphere, and we get like one projection, right? Like one view onto this blob. What we want to do next is we just add noise to it, right? So we know that like diffusion models, they just do denoising. So let's artificially create a task for our diffusion model. So we'll just add random noise. Then we'll take a pre-trained 2D diffusion model, right? So this model was trained on this like billion-size image data sets, and it knows how to denoise images. And that's exactly what we do. We give it a noised image. And what it does, it denoises the image. So it returns as a blob, but because you cannot really like exactly reconstruct the same blob, it's going to be a slightly different blob, right? Like it's going to be modified. And so what we're going to do next, we will take this slightly modified blob from the diffusion model and just backpropagate it to the 3D representation. And we'll see what happens. And it happens, for some reason, that if we keep doing this procedure, we'll iteratively generate a 3D shape. So I can probably skip through a slide before jumping, and so like this is the results, right? This is what this original work offers as a result for 3D generation. You can see like for a corgi, for instance, taking a selfie, there's like a dog, and it's a 3D shape. You can rotate it, render from different angles. There's like a frog. So you can really like generate 3D shapes, and they have meaningful geometry, right? So like, if I can show you, so this is usually a normal map, just like tells you how the actual 3D shape looks without the texture, and this is the opacity map. But like, basically the idea is that the 3D shape is actually meaningful. You can take it and pass it into a video game, or you can take it and pass it like in a video production pipeline. But maybe we can go a little bit back and see like step by step how exactly it works. So in score distillation, right? So like in the heavy explanation, we like render random camera, add noise, denoise, and backpropagate. But if you look into the algorithm that the author provides, there is like one interesting formula, right? So what's happening here? We have psi. These are just like parameters of our data structure that represents a shape. And this is what we can change, right? Like if you change this psi, the 3D shape changes. Then we have a set of cameras, just like we can sample like multiple orbits around the 3D shape. We have a text prompt, y, that what we want to generate, for instance, a corgi taking a selfie. This function, like it's a function from Rn and C to Rn times n. This is just a differentiable renderer. So this function takes parameters of the 3D shape. It takes the camera position, and it gives you the image, right? So this is like how we get an image giving our 3D structure. And the whole point of this 3D representation is that G is a differentiable function. We can backpropagate gradients through it. And finally, we have epsilon theta. This is our pre-trained diffusion model that can take an image, a noisy image, and return another image with like the noise that we should remove from it. And what's important is like theta is fixed. We are not optimizing the weights of the diffusion model. And then what we do, we just randomly initialize the shape and then keep iterating over this loop. On each step, we randomly sample T. So if you remember, unlike DDIM or like DDPM, whenever we generate images, we don't really have a schedule on T. We just randomly sample it. So imagine we randomly sampled somewhere like on a certain noise level. Then we randomly sample a camera around the object, randomly sample noise. So we basically randomly sample everything, add this noise to the rendering. So like you can see, we take the parameters of the 3D shape, we render them, it gives us an image, we rescale it, add the sampled noise, and we get a noisy image. So like we get this thing. And finally, there is this formula, which says that the gradient of some loss function, and we don't know yet what this loss function is defined as the difference between sampled noise and the predicted noise, and then rescaled with like some parameters. And so what we do, we take these gradients that are defined by this magical formula, and we just plug them in as a direction of improvement for this image, and backpropagate. Right? So it's like kind of an important detail that we don't have a loss function that we backpropagate through. The initial score distillation formulation gives us the gradients directly, that we just like plug in as gradients of the image. And just to zoom in, this is the formula, right? Like super simple, just like difference between predicted noise and the added noise. So I'll probably pause here. If you're like lost or tuned out or have any questions, please don't hesitate. This is kind of like the most important slide of this lecture. So yes, please.
Are we generating like the representation of the object?
Yes.
Like the thing that's inside the block picture?
Yeah.
That's what we're generating.
Exactly. So we are optimizing for C, which is kind of like a latent code for this data structure that in the end represents the 3D shape.
I see.
So we're generating a 3D shape. Mm-hmm.
This is not necessarily at all like a 3D shape as we would have in the games.
It can be. So like, for example, right? Yeah. So these are examples of 3D shapes you can generate. I mean, it's a different representation. So usually in video games, people use triangle meshes. This is a representation that's called a nerve. It's like a volumetric representation. But it doesn't matter because you can convert from one to another, right? So like the main property of this representation is that it's differentiable. And as soon as you got it, you can like extract like the surface, you can extract triangle mesh, like whatever, and plug it in your favorite destination. Yeah. Any other questions? Yes, please.
I was just wondering, how is it different from other approaches? Because it seems like the loss function and backpropagation are kind of common usage across this approach. So what's different about this particular?
You mean about score distillation?
Yes.
Versus what?
Versus just general, like a neural network, you're using like forward propagation and backpropagation, and you're just comparing loss functions, all the many of them do. So I'm wondering what's unique about it. Is it maybe the approach is similar, but maybe how we choose epsilon is different? Or
Yeah, it's a good question. Well, so this is actually quite far from like a typical neural network training, right? So while we have gradients here, don't mistake them for neural network training. So instead of training the neural network, like we have a neural network here, right? But it stays unchanged. So it's per se more like test time optimization versus training. So like these weights are not changing. What we are changing the 3D representation. So instead of training a model that will generate 3D shapes, we are basically like optimizing the 3D shape, giving a fixed 2D image model, right?
Does it add a layer of dimensionality that makes it unique?
Not just this, right? Like the fact is that we are fixing the model. But I think the most magical part here is that if you think about it, this model has never seen anything in 3D. It's like it's got no idea what depth is. It's only seen like flat images. And then all of a sudden, it's being able to generate things like this. So like all of a sudden you get like a corgi in 3D where like there is a depth, you can like rotate it. While the model, there was like not a single data point that is view consistent or 3D. right? So I guess this is like the most exciting part about this, is that you take it from one domain, which is images, and you can use this image model to generate 3D shapes, which is completely different domain. There are like so many more complicated things you have to consider, but it still works somehow, right? So score distillation is like, you can think about it as basically, and this is why it's distillation, right? I'll give you a little hint. It's distillation because you're kind of like distilling the knowledge from one domain about images to apply it to generate objects in a different domain, or like on a different task, right? I hope it answers the question. Yeah.
And I'm wondering in terms of the weight, because we're learning from the 2D images with the noise and denoising, and then going to 3D image. Does the weight, when we're doing 2D to 3D, do we change the X, Y, Z, like the weight distribution, or is it use one weight to transpose it from the 3D image onto from the 2D to the 3D?
Can you repeat, please?
So we're learning something about the image from 2D,
Mm-hmm.
and we're transforming that to 3D.
Mm-hmm.
But 3D, we have X, Y, Z axes.
Mm-hmm.
Each one of them can have a different, in terms of weight.
Mm-hmm.
So it could be one axis has to do with the shape, one other axis has to do with the line outline of the image. Do we give them? How do we alter the weights for those? Do they have to be equal? Meaning the weight I use for x-axis is the same as the weight I use for y-axis.
Mm-hmm. Yeah, well, this is a good question, and I think for that you really need to understand a bit more about this rendering function, because this is where the magic happens, right? All this right part, it's still like we operate in the domain of images. We like get the gradients, we like propagate it back to the image. So there is no third dimension in this right part. When the magic happens is that whenever we backpropagate these gradients back to a 3D shape. In that case, we unproject the gradients from the image back to 3 dimensions. And so like you're right to ask about the third dimension, right? Like how they're weighted. So the 2 dimensions that you like, imagine I'm looking into like this clicker, right? And this is my camera angle, right? So you can see that like I'm generating an image that is just like a flat projection of the clicker onto the plane of my camera. In that case, these 2 dimensions, they're going to be like equally weighted. So I just like insert the gradients and I change the image from this perspective. But the depths, I have no knowledge about the depths. So even if I supervise this like one view, like I'm not really changing anything about the depths. It can be like arbitrary. But the whole magic is because I'm resampling the camera position, right? So like instead of staying stationary, the next iteration is going to be a new camera sample. So I will be like somewhere here, right? And this is kind of like a different perspective. And in the object coordinates, it's going to be different projection, right? So this is what supervises the object. Yes.
I'm a little bit confused. You said the diffusion model for the 2D part is fixed.
Yes.
Right. So what is this data that you're optimizing?
Yes. So theta are the weights of the diffusion model, and they're not really changed. Psi are the parameters of the 3D shape. So you can think about like if you change the psi, this blob will morph into something.
Like what she mentioned, the XYZ is equal, the 3 dimensions.
Kind of, right? So like the 3 dimensions is just like where the 3D object exists, right? So like this clicker is 3-dimensional, right? An image of this clicker is 2-dimensional, right? But psi is basically like, imagine we take psi is like some collection of numbers, some latent code. If we change some of the coordinates of the psi, this clicker will like get longer, or it will get like change color, or it will rotate, or it will like morph into a sphere.
So it's some representation of the 3D object.
Exactly.
And usually how do you represent that?
Yeah, so I think it's a little bit outside of the scope of this lecture. I can share additional materials about this. It's a very good question, and there's like lots of research in this. And there are many different approaches with many like pros and cons. This particular one is called a NURF. It's called a neural radiance functions. And the idea is it's a volumetric differentiable representation. And I can share a paper later about it. I'll include it into the email later. Yes.
So well, this approach is basically just like using the diffusion model to like linearly scale this like gradient with respect to G. Like there are no gradients like directly flowing from the diffusion model to the NURF representation. Is that right?
so just like to iterate for listeners, the question is that like this approach is linearly scales the gradients from diffusion model to the 3D shape, and there is no direct gradient flow, if I understood you correctly.
Like it's like linearly scaling the sigma g over sigma p. So there's no direct gradient directly flowing from the diffusion model to like the nerve presentation.
Well, yeah, it's flowing, but through G, right? So it's being projected through G, but it is flowing. I'm not sure if it answers, yeah. Yeah.
Is it the nerve is never trained, right? So is it possible to also use like other forms of guidance, like a classifier or something, instead of a diffusion model? Like, is the diffusion model very important here for this guidance, or are there like other ways of maybe using like, I don't know, some contrastive like covariant approach, maybe with a classifier or something?
Yeah, so the question is that can we, instead of a diffusion model, right, because like diffusion model just gives us gradients, right, and it sounds like we can take the gradient from like a classifier or some contrastive approach, can't we do the same without the diffusion model? And I guess, I just didn't see many works in this area. It might be a very interesting research question. There are definitely GANs, so like to your question about contrastive learning, like maybe adversarial learning, there are GANs that generate 3D shapes. They are not that successful compared to diffusion-based approaches. But I think there are like a couple properties of diffusion models that hopefully we'll get to today that I think are very important that actually like makes it so good.
But overall, is the idea to have like some form of guidance that like makes the representation be optimized to be consistent and mapping to the prompt from different viewpoints? This is like the idea.
Yeah, this is really the idea, right? So like it's very simple, right? You have like you just optimize the 3D representation with something that moves it towards the prompt. You can, if you have a very good function that moves your images towards the prompt, you can replace diffusion model with this function. So yeah, exactly. Okay, before you ask any more questions, let's probably move because it's already 10:30, and it's only 10% of the slides. Right, so we can get results with this. The results, you can probably see that they're like a little bit short compared to what the image diffusion model can do. They're like a little bit oversaturated, they're like super colorful, a little bit like cartoonish, toyish. And there is like a reason for this, which is basically because the first work who introduced this, we don't really know where this objective function comes from. And it turns out that like this exact form of this objective function tends to oversaturate and like make the 3D generations a little bit cartoonish. There is another work. There is actually not another work. There are like so many works. So this thing came out 2 years ago, and since then, like probably every week, there are like 5 new works that try to fix this. The prolific dreamer is one of the most famous ones. We'll jump to it in a second. Noise-free score distillation, but like many of them. I also tried to jump on this train. So a very famous one is called variational score distillation. Oh, and just like for reference, this first algorithm, it's called, so like the whole field is called distillation. But the particular algorithm that we went through, it's called SDS, or score distillation sampling. So there is like a little confusion about notation, just like know that SDS is a particular algorithm. Score distillation is kind of like a collection of all these algorithms in the entire field. So another particular algorithm is called variational score distillation. So you can see it here, or VSD. So if this magical formula in score distillation, how we get the gradients, it looks like just a difference between predicted and added noise. The magical formula for variational score distillation is a bit more complicated. And it's actually even more confusing. Like, if you're curious about this field, I would really encourage you to read variational score distillation paper because, I don't know, it made me think a lot about this whole field and inspired my research. But basically, the notations are a little bit different, but like what's happening here, right? Like this is just a scaling term. This is our gradient of the rendering function back to the parameters of the 3D shape. So both of them, they have, so like here, the notation is a bit different, but basically these are the same 2 terms. And the weighting also like different notations because from different papers, but these things are the same. So where the difference is in what is actually like between these braces. In the first case, we just like sample random noise term added to the image, predict the noise, and then takes the difference between predicted and added noise. Here we do something much more complicated. We take this epsilon, which I just sampled, we add it to the image, we denoise it with our pre-trained and fixed diffusion model. But at the same time, we also have a second copy of this pre-trained and fixed diffusion model that is fine-tuned at every step of our update, and is fine-tuned to denoise our current 3D shape. And so this second copy of the diffusion model that is actually fine-tuned also gives us a prediction of the noise. And then the difference between these two is taken as a gradient. It's kind of like super confusing. And the derivation of this also made me like, I was extremely confused. But like, why the hell would we fine-tune it? Why would it work? And the results are actually very impressive. So you can see how we jumped from this like cartoonish, a little bit oversaturated 3D shapes to something like this. You can actually go to the website of this paper, and you'll see them, like you can rotate them in 3D and see how detailed they are. But there is like an insane amount of details. Like the geometry of the 3D shape is very good. All the shadows are very good. Like it just looks amazing, so much better. But the question is like why? Like it's completely not clear why this would work. So I'm afraid we really like being too slow. So you'll have to probably skip through one of the derivations, but let's try to go through one of them at least. So how did we obtain this magical formula in the first place? So can you raise your hand if you remember the loss function we used to train the diffusion models, approximately? Okay, no? All right, well, then let's remember. On the first lecture, Chenyang prepared these beautiful slides with different colors that I just stole from him that basically explain the training procedure. So the our denoiser neural network, epsilon theta, it's a function from some function from what? Rn, I guess, is an image, and R plus is a time step. It maps us to another image, right? And so the way how we train it, we just our loss function is an expectation, which in practice means we just like randomly sample these three parameters. And these three parameters are initial training data sample from the data set, sigma, which is just the noising, it's a scaling parameter according to our noising schedule, and epsilon is just like an instant of random noise. So we sample all these three things, we add them together to get a noisy image, we feed it into our neural network, and our training loss is just basically L2 loss between the whatever we predicted and whatever we added. So very simple loss. And so this function, it's called score matching. Because like if you remember at the beginning I mentioned that in diffusion it's all about scores, which is the gradient of the logarithm of the probability function on the image space. And it turns out that the score is also the noise. So the noise term is a score. And so we kind of like match the scores together with L2 loss, and that's our training objective. Okay, so why don't we try to derive this weird formula? If you remember, weird formula from the score distillation was also something similar, like the difference between predicted and added noise. So maybe there is a connection between the two. And why don't we try to derive this gradient through this objective function? So we start with the same, right? Like we sample noise level, sample the noise itself. Like there is some scaling factor, there is predicted noise that comes out of our neural network, and there is added noise. Cool. So this is our score matching that I just rewrote in notation that I like more. We start with this. We take a gradient, right? So we calculate the gradient of the expectation. Expectation is linear, so gradient goes inside. This is a linear function, so WT goes outside. This is a L2 loss, so we get 2 somewhere it's just a constant, so whatever. We get the difference between the two, then the gradient of the diffusion model with respect to the input image, and then the gradient of the input image with respect to the parameters that parameterize this image, right? So basically, if you remember your calculus, just very simple calculations here. All right, so we got this, but then there is a caveat. So in the original paper, authors claim that apparently it's much better to just do this. So what is this term, right? This term, again, is a gradient of the output of the neural network, of the diffusion model, which is a noise image, with respect to the input image. And so, strictly speaking, it's a Jacobian. So it's like a giant matrix of like n squared by n squared parameters, where like each pixel is of the output image differentiates with respect to the each pixel of the input image. So it's like a giant object. It's very heavy to keep it in the memory. And the authors just like say, all right, let's drop it. Right? So like the Jacobian is basically determining how fast or like how sharp is your function of the denoising in a particular noise sample. And what we do is we just say its identity, meaning that like it does nothing. So we just say, why don't we assume that like our diffusion model does nothing? And then we end up with this update rule. And so this update rule is exactly what is used in score distillation. But it's kind of like a very wild assumption, right? Like, why do we assume that the giant trained neural network that generates images, has like some logic in it, has a Jacobian of identity, which means that like it basically does nothing. And moreover, if we like try with Jacobian, it kind of like doesn't really work. Without the Jacobian, so like whenever we dropped it, it starts working. So it's like a big mystery why. So maybe that's not the correct way of deriving this. Then there is another perspective. So what if we start with Kullback-Leibniz divergence? Has anyone heard about the KL divergence loss? You're here. Okay, a couple people, yeah. So basically just, this is a loss function that's defined on two distributions. And we can match the two distributions with each other. So I'll probably like skip through some of the slides, but basically the idea is that let's try to see like, what can we try to optimize here? So this is the loss function that they proposed. It has two distributions, right? So the K loss is defined on two distributions, Q, and this is distribution of the images from our 3D shape, right? So if I take my phone, like there's so many cameras I can sample around, it determines the distribution of the projections of this phone somewhere. So this is our Q. Then, well, ZT is our noised latent code for the image. So like after we took the projection, we can noise it and calculate the probability of this noised projection, given that our denoised projection comes from the one of the projections of the 3D shape. So this is the left distribution, right? Like how likely is this noise sample if we assume it was sampled from the projections of the 3D shapes? And the second term is that, we kind of like know that the diffusion model kind of learned some distribution. It was trained to learn distribution in images. So even though we don't have a direct access to this distribution, but it contains knowledge about how likely each image is and how unlikely it is. And so this distribution that the diffusion model learned, it's P, phi. I know we keep changing this parameter's name, but it's just the weights of the diffusion model. And the distribution is conditioned on our text prompt, right? So like in this case, it would be a smartphone in the classroom. And the diffusion model learns distribution of all possible images of smartphones in the classrooms. So this is kind of like what we try to optimize. Let's start with this loss. And then there's like some math, and then more math, and more math, and more math, and whatever. Basically, the story is the same. Like after we do all this, we kind of have to drop one of the terms. And one of the terms happens to be a partial derivative of one of the distributions with respect to the image. And if you don't drop it, it doesn't work well. If you drop it, it works well. And so the question again is like, why? What the hell is going on? So here is like, there is some intuition behind that. I'm not sure we have much time, but I'm happy to chat more about this. But basically, we're ending up in this interesting situation where, okay, we have this score distillation update rule. If we don't drop this last term in the KL derivation, then this function that we will get for the gradients, for the fair gradients that should go to the 3D shape, is going to look like this. It's going to be like expectation of just the denoising, just like the noise predicted from the model, times the gradient of the differentiable render. So like, this is just the formula that we get in a fair way. But if we actually try to generate something with this, the results are like very so-so. They're like super noisy, they get lots of artifacts. So if we actually drop this term in the Kyle derivation, then we get minus epsilon. So we kind of like, instead of just backpropagating the predicted noise as a gradient, we propagate the difference between predicted and added noise. And then the results, they get much better. They're like less noisy, there is less artifacts, the shape actually looks better, everything's good. But if we do something even more weird, right, like variation score distillation did, if we take a copy of this diffusion model and like train it on, fine-tune it to denoise this particular object, and it's going to be like much more complicated object. Now we are taking difference between pre-trained model and the fine-tuned model noise predictions. In that case, the shape, like the results are much, much better. It's like, basically, yeah.
You might have already talked about this already, but how do you think you'll actually implement the fine-tuning piece of the practice? Because it seems to me like you have to fine-tune it on every single input you want.
Yeah. Yeah, so unfortunately it's also a little bit beyond the scope of this lecture, but the way how they implement it in practice, they use LoRa's. How many of you have heard about LoRa's? This is called low-rank decomposition. So basically the idea is that if you have a giant neural network and you want to fine-tune it, but you don't want it to forget stuff, you don't want to spend too many resources fine-tuning it, there are approaches that just allow you to fine-tune like only some parameters in there, such that it doesn't forget. That's what they use. It's like a little bit less expensive. It still is much slower to do this, right? Because there's like a whole fine-tuning step. But the results are much better. Oh, and also like in terms of how long it all takes, it's already taking like 1 hour to generate these previous shapes, right? With LoRa and like this fine-tuning, it takes like 2 hours. So it's not like instantaneous generation where you like immediately get a 3D shape. It's, you input the prompt and then you forget about it for a while. Then you come back and you have the shape. So it's kind of like doesn't matter that much. We're not like competing for real-time generation. So that's basically like a interesting question. What's happening with this term? Like why is it behaving the way it is? And I kind of have an answer, but I don't have time to go through it. Oh my God. So there is a thing in statistics. I actually recently learned about it not from a statistics class for some reason. It's called control variance. And it's a very interesting approach for mean estimators. Maybe I can quickly say what it is, because I think it's a very interesting approach. So imagine you have some parameter mu. So like you're sampling from some distribution, for instance, distribution M. And you just like want to estimate what's the average of the distribution, what's the mean of the distribution. But the problem is that M is kind of super noisy, and you don't have that many samples. So how do you estimate mu in the best possible way? So then you can use this control variance. Imagine that you have a second distribution, like second statistic, T with the mean in tau. So if the second statistic somehow correlates with your first statistics, you can use this information of correlation to denoise your mean estimator. So in particular, if you know the mean of this, the original mean of this T samples, you know that like if you take one of the samples M and add a constant of a sample T minus its mean distribution, you know that on average it's not going to change the distribution of the mean of M, right? Like mu is not going to change because this is on average is going to be 0. But the thing is that because if T correlates with M, you can choose C with this magical formula, which is like something variance, covariance, whatever. The whole idea is that C basically decorrelates M. So if you can imagine that like M is just crazy statistics that just like jumps across the entire spectrum of its values, using this correlation between the two, you can kind of like reduce the variance. You can make it jump less. In that case, you don't really change its unbiased estimator of mu, but it also has a much lower variance. I mean, it depends on the correlation. And so probably the answer for like this second term is exactly this, right? We are trying to estimate, this is exactly what we're trying to do, right? Like we're trying to estimate the average of some statistic, which is noisy because it's a complicated function. And then we subtract different statistics with coefficient 1. So one of the ways to view onto this, like what's happening in this entire field, is that we just try to reduce the variance of the gradients. Right? It's like the original gradients that we get from the Fair derivation are super noisy, and with all these approaches, we just like try to decorrelate it, denoise, and reduce the variance so that we have a better approximation of the gradients. Right. I really want to go to the second part of this. So there is another perspective, and I think I found it quite intuitive. So let's look into that. How can we like get this feel for score distillation through this view? So remember how like there are two parts, right? Like this left part is just entirely about 3D representation, how we take a 3D shape, how we render, and it really is like kind of detached from the right part. The right part, as you correctly mentioned, is basically just a guidance, right? It's just something that gives us gradients on the image to make it aligned with our prompt. So we can like swap these parts. So if we heard the suggestion to swap the right part with something, let's see what happens if we swap the left part. In theory, we can just swap it with some kind of image representation, right? We have like a latent code, Psi, we have some decoder that just represents an image basically, right? Or it can be just like pixels of the image directly. So in that case, this whole approach of score distillation with this magical function will be basically just image generation, right? Because we optimize parameters of an image. And so in that case, we can compare the quality. How does, for instance, DDIM or like all these methods we covered in lecture 2, how do they compare to score distillation when we actually optimize the image? And the answer is that it's not really in the favor of score distillation. So you can see here that like this is DDIM. This is like a hamburger we get from there. This is a hamburger we get from these magical formulas. So something is like really off here. And there's definitely capacity to improve all this. Well, what we'll try to do is basically replace this right part, the guidance, with something similar to DDIM. So like, we know that DDIM is capable of generating good samples, so why don't we use DDIM as a guidance instead of this weird formula? So let's see how we can do it. Just a reminder what DDIM is from, I believe, second lecture by Cole. DDIM is just basically a deterministic way of sampling images, right? Like we have the DPM, which is stochastic, we have the DIM, which is deterministic. And the idea is that after we train the diffusion model, we just sample noise and gradually remove this noise from the image. But the very important part here is that we operate through X naught, which is like on each step of taking the noise back, we kind of like, we can take all of the noise and generate a single step denoised image. So let's look at it. Imagine this axis is our data dimension. So assume our images are just like one-dimensional, meaning they have only one pixel with one color. This axis is going to be the T in diffusion modeling, right? So this is like how much noise we add. And if you're like all the way at 1, this is like completely noisy image. It's like just Gaussian noise. And this is going to be like completely denoised images. So like our training data set lies somewhere here. All right. So if you have this, how does DDIM look like? At first we sample a completely noisy image, right? So it's going to belong somewhere like at the bottom, like on one of the coordinates of this axis. All right, we sample this noise. Then we take our pre-trained diffusion model and predict the noise to remove. And it gives us some direction in this space. And we basically remove a little bit of this noise, right? Like we, this is like one update step of DDIM. We just moved a little bit up, so like to a less noisy image, right? And we'll get something like this. So you can already see there's like some signal appearing through the noise, and we call it like X bar of T2. Cool, and then we do the next step. We probably already can guess what the image is. And finally, the last step is like completely removes all the noise, generates the high frequency details, and we get the cat. Nice. At the same time, whenever we did the first step of DDIM, what we could have done instead of removing just a little portion of the noise, we could have removed it all the way. And so the way how it would work then, we would get something, right, like single step denoising, so we'll get like a completely denoised image, we would guess something like this. And so this is the reason why we don't use diffusion models in a single step, right? Like they just don't work. And hopefully from the lecture yesterday, you probably got some intuition why it's the case, right? All right, so this is what we can do. But you can probably still want to keep generating this image, right? Still want to improve the cat. So what we'll do from this image, we can return the noise back. So we say, like, okay, we didn't generate enough, so let's return some noise back. And let's call this noise that we add back to the image kappa. It's also a function of the prompt, and it's a function of the T3. So we just like remove the noise back, and we end up in the same point as DDIM. And then we just keep doing this. This is the second step. It's a little bit disturbing sometimes. But the fact is that like we just keep improving the image, right? And it's basically the same process as DDIM, right? So DDIM, you're like just existing in the space of noised images. But what's interesting is that now we just defined a new process, right? So you can think about this like intermediate variables x0 t3. It's still the part of the same process, right? Like we always been coming back to the same intermediate values. But it basically determines a new process. And this new process, it exists in the space of denoised images. So you can see, right, like if DDIM is just like defined on the noisy images, here we kind of like evolve our image from blurry, slightly disturbing to something much better. Like we evolve it to like sharp, actually good-looking images. While it's exactly the same process, just like reparameterized to this new variable of x0. And this is kind of like the whole view that I wanted to share today onto score distillation, right? Because what happens next is that let's make it a little bit more formal. So I'll skip the formulas, but the idea is that if you like write the definitions for all these steps, we assign to kappa just like the same noise term that we added on the previous step, and then we do this is like the formula that kappa should be. And what's interesting is that if we look into this formula, epsilon or kappa appears twice in the formula. So basically epsilon should be such an epsilon, or like kappa should be such that whenever we run diffusion model on the image noise with the same epsilon, it gives us the same noise back. So this equation is called stationary point equation, right? So basically like a point, if you call this function on this point, it doesn't change the point. So if you basically pick the kappa to be a solution of this, or more like simpler, it just should be epsilon from the previous step of the generation process, then we'll end up with a formula like this. It's a little bit long and scary, but there are, we can simplify certain parts of it. So let's look what this formula does. There are two parameters, right? So like x0 t minus tau and x0 t. This is basically just like the steps on this top line of our plot. This is like previous blurry cat, and this is a slightly less blurry cat, but both of them don't have any noise. And so basically this formula just provides us an update how to go from blurry cat to less blurry cat. All right, cool. The right part is basically a rescaled version of a difference between predicted noise on like something, we'll go to what it is, minus the kappa that we added, right? So you can probably already sense like some common noise here, right? And if you look into what epsilon is running prediction on, it's basically just our current cat plus the added noise. Right, so again, like the entire right part is just the difference between the predicted noise and the added noise. And I know I probably lost some of you already, but does anyone know where it's all going? So like, right, we took DDIM, we reparameterized it, we got this formula. And then we can also say that kappa, it's like a little bit complicated where we get kappa, but if you just like randomly sample it, does anyone want to say what it is? What this formula is identical to? Maybe there are like some intuition here. Right, so like just an update rule that gives us like some kind of gradients that's equal to rescaled version of predicted noise minus added noise. All right, I won't be torturing you, so it's SDS. So this is like the score distillation thing. This is exactly what we are trying to derive. And if you remember the first two derivations, in this case, we didn't really drop anything. There was no like weird parts where we assumed that Jacobian is identity. There was no part where we assumed that the partial derivative doesn't exist. We just like fairly took the DIM, reparameterized it, and got the exact update formula. With one caveat though, so there is still, there is one sketchy part. We assume the kappa that we added is not really a solution of this stationary point equation. We just randomly sampled it. In that case, it's exactly SDS. But the beautiful part about this is that if we actually take a better approximation of kappa, doesn't really matter how we do it, but we can just find a better approximation of the kappa following this equation. Instead of randomly sampling it, we will improve this first paper that generates cartoonish results. So even though there was like a sketchy part in this derivation, if we kind of like don't do this sketchy part, we get much better results, and we can generate something like quite realistic. For instance, something like this. So these are like 3D shapes you can generate with this reparameterized DIM. But basically, we have less than 5 minutes left, so I think it's almost perfect on timing. Basically, if you had to, if you want to read more on this like kappas and correct noise sampling or whatever, there are a bunch of works. This is a very interesting one where they suggest to generate noise sample that is like kind of consistent in 3D. So like you can take a noise sample, but then if you generate the same noise sample from the side, it's going to be like deformed consistently. I think it's a very beautiful idea. But in any case, if you had to take one thing away from the day, right? Basically the whole point is that if you have a trained diffusion model, by all this like reparameterization or whatnot, you can just use this trained image diffusion model as a source of semantic gradients. So you don't have to always use it on like denoising task, right? You can reparameterize it in such a way that it gives you direction on any image that will improve this image or like move it towards a prompt. And you can really plug this thing into many applications, right? So this is what I just said. But basically, into different applications where you can plug it in, for instance, imagine you start with one image, and then you take this pre-trained denoiser, but then you reparameterize it in a clever way, and you apply these gradients with a different prompt, right? So like you start with an image of a statue, and then you apply these gradients where the diffusion model is conditioned on a prompt, a statue with raised arms. And just like keep evolving this. And if you do this, you just like obtain the deformed image. So like you get a statue with raised hands, right? Another approach is like not really published much, but I think it's quite interesting to consider for potential research, is that imagine we take some initial image, right? And this image is probably like just a normal Toyota RAV4, right? It's probably quite likely under the distribution that our diffusion model learned. But what if we make some distortion to it? So here, I'm not sure if you can see because of the contrast, but I just like removed a single square from somewhere in the image, right? So in that case, it's very unlikely that the diffusion model have seen something like this, right? Now this image contains an artifact. So what if we take the gradients from this reparameterized pre-trained diffusion model and just see where these gradients are big, right? We'll try to like evaluate what would be the first thing the score distillation tries to fix in this model. And if you just like numerically evaluate these gradients, we'll get that like they're very big in this area, right? Like there is not that much that we need to evolve in this area, but since this is kind of like a weird spot, the first thing score distillation will try to do is like fix it. And so maybe we can use it for some kind of like anomaly detection, right? You can see what's going wrong. You probably like don't know what exactly is going wrong, but your diffusion model can hint you like that certain parts of your image are not really aligned with the distribution and even like localize them, right? So I think that's really it for today. I guess like really the main message is just use diffusion models. They're like super flexible for many applications. There are lots of exciting things you can do with them. And yeah, I'm happy to chat, answer any of your questions after, and like feel free to reach out. And yeah, thank you a lot.